So one of the biggest things I have to discuss a lot of times to people who are talking about data recovery and trying to figure out what this is, the common people who aren't doing forensics and who haven't been doing a lot of hardware stuff for a long time is, in their mind they think data recovery is, I am just running some software. That all I did was go out and buy some software or go download some software online and I run that against the drive, I build a pretty tree, and I extract some data. That's what people believe is our job. So when we're doing data recovery, even forensics in some cases, they think it's like that, it's just a little bit harder. Like that's literally the response I get the majority of the time. So one of the things I just kind of want to bring up right up front so that people kind of get this rather than hit this at the end of the day so that this idea is a little bit fresher is, so every hard drive and every computer / controller, motherboard, all the components of the computer, they have a way of communicating with each other. And it's evolved over time. It's a very old protocol, been around for quite a while from a standpoint of how to communicate with the hardware. And so in the early days, there wasn't as profound a way of communicating with equipment. So there was a method of communicating called programmed input-output mode. And that's basically everybody, it was kind of like being a cowboy. Like it was all a variety of different ways. Everybody ran their own shop. Everybody did something different. And hard drives didn't work together. They weren't compatible with each other. The controller cards weren't compatible with each other. So there was a really difficult way of communicating with these things. And you could walk into any scenario and it would be different. And I did. I actually worked on a lot of this stuff back in the 80s because I am that old. And there was a variety of things that you had to know or deal with. You had to have specific controller cards to do specific types of things when there was hardware problems. This is where Norton started out writing his utilities to deal with some of the problems. So the idea that I want to get across is primarily this, that the hard drive manufacturers and the controller, which at the time was in many cases actually built onto the hard drive, so it was from the hard drive manufacturer, have an agreement. How are we going to communicate with each other? And so eventually somebody says, well, we need some standards. And so the standards are primarily done now by a group that's T13 is the name of the group, and they basically run the standards committees. And it's a group of people from Microsoft all the way through Intel, through large other groups of people who try to make decisions about how our future is going to be and what's going to happen with hard drives. But back then it was pretty hard to create a committee, to create stuff, to get everybody to agree, and then they finally did. So we have an ATA standards committee. Now, ironically, at least the ATA, at least from looking at the technology and what it stands for, is the AT attachment. So it's based on the IBM PC's functionality. So the IBM PC's functionality from the 80s still didn't evolve into anything until 86, 87. So we're talking 82 to 86 or so that they started to evolve. Then we still had programmed input-output mode that lived for a long time until we finally got into some ATA standards. Now what this is there is a chip on your hard drive and a chip on a controller, and those two have to communicate with each other. So you send commands to the controller, and then the controller talks to the hard drive. So you may send a more simple command to the controller telling it a function that you want to occur, and then it has a subset of commands that it knows that it can send to the hard drive. And that's how they exchange information and go back and forth. The problems are really that hard drives still, even today, can have a huge amount of commands that are specific to those hard drives, to that particular model, to that particular brand. They can make it do whatever they want it to do, and there's just a group of them that are standard that everybody can kind of use. So when you're talking through Windows, and you're using Windows to communicate with your hard drive, it uses an API, and it's available to programmers to say, I would like to transfer a block, or I would like to transfer a sector, or I'd like to write something to the disk. And those APIs are all going to be pretty standard. The difference comes in when you actually have other hardware you want to do more extended things to. You want to transfer data directly, or you want to bypass an operating system. So Windows and its commands are very generic. It's very boring. It doesn't really say, oh, if you have a Western Digital, let's do this. If you have a Mac Store, let's do this. They're just generic API commands. So when you download software or you use software that's doing data recovery content, that's all you're doing is using something that's making mostly, almost, there's a few exceptions to this, but the majority of them are all going to make an API command to the Windows/Mac OS or whatever else the OS is there, Linux, and it's going to make a request to the hard drive. So it's very simple. There's some timing mechanisms that happen. For example, Windows doesn't like anything that takes longer than 600 milliseconds. If something takes longer than 600 milliseconds, it will just fail. And it'll just say, oh, I'm sorry, I cannot open this spreadsheet, or I have a problem, CRC, something explodes, or the system crashes and blue screens. So there's some very simple things. Everybody who tries to do data recovery out there that has no idea about this hardware or any of the stuff we're about to do in this class, because I pretty much skip all the regular generic stuff that everybody would just click on. I just really don't cover a lot of that because there's no reason to. That's the reason that you're here, is because all that stuff usually fails. And so from that perspective, all they're doing is using this really horrible system for trying to do a recovery. They'll plug a hard drive in through USB. They'll try to get some data off of it through the Windows API. USB is a whole other set of problems. USB in and of itself, until we get to USB 3, USB 3 finally gets intelligent. Prior to USB 3, and it's more like an Ethernet protocol by the time it gets to USB 3, that you have a protocol, you're making a request, you can talk to the drive, and you can do certain functions. Still not all the functions that you can do if it was connected to a controller directly to your system. USB is a very low-end, somebody bought a chip for a nickel from whoever the lowest vendor was that would sell something, so it doesn't know error correction, it doesn't know how to communicate with specific drives, it doesn't know how to pass commands. USB is, again, a very generic driver-driven protocol. Inside every operating system, if you want to talk to a device that's USB, it must have a driver. So your system may have a generic driver for it, like a mass storage driver, which is what is really there inside of Windows, very similar in Mac OS, and then they're just emulated. There's just copies of them basically in Linux, because they're trying to make all the stuff happen that works in PCs happen in Linux. So your communication is very limited. You have no real control. So USB is not a way to do data recovery until you at least get to USB 3, where you can actually do it. All the other stuff is going to be very generic, and you hope for the best. That's really the way it goes. So my personal opinion is you should never be looking at a hard drive that you're just going to pick up and say, I'm going to plug this into a Windows system and try to do a recovery. That is not the best way to do this at all. So there's a number of different ways we can deal with now. Now, when you get to USB 3, right now, for the most part, if you're doing recovery, we're talking very specialized hardware. Hardware has started to add these USB functions and the ability to do them raw with just a USB device. Just plug it straight in and work on it. Up until, say, 2012, 2013, we had no hardware that could do it at all. There was no way to do it through USB that was efficient. Everything would fail, basically. Anything that was going to happen, you plug it into Windows, it's going to do the same boring thing, it's going to fail. So what we would have to do is break the hard drive to fix it. And what I mean by that is, what happened is a lot of vendors decided, again, vendors are going to make really bad choices for you, for them to save a nickel. That's all that's going to happen. On every platform, every way you look at this, they're going to make bad choices for you to make it better for them, and then try to convince you that they made it better for you, which is just not the case. So when you go out and you get a Western Digital passport drive, just a passport drive that has a drive that's on a card, basically, they remove all the connectors that you would have had that would have been SATA. Until 2012 or so, we had drives, they had a SATA connection or they had a physical connection, and then you plugged in a USB adapter and put it in the case. That's not how it works anymore. Now those drives, the card itself, they basically have SATA on them. They're still there. They just remove the connector, so you no longer have the piece that helps you connect to that point. They just solder the USB connector straight onto the board and then bypass the SATA connector. So you always have a manual way. In all the USB devices right now, you can still break them and learn how to solder wires to the appropriate places and make those devices work. It's not the easiest thing to do, and you don't always know the exact layout of what the pins are. You a lot of times have to hunt somebody down that knows them, or look it up online, or go find it. So it makes it a lot easier if you have a device that can handle USB directly. But otherwise, what you're trying to do is get back to the SATA interface so that we can communicate with it using some of these methods. So just to kind of go over the idea here of what we're doing in data recovery and what makes us different as a core, just the small subset of the things that we can do, because there's a huge amount of content that we can actually deal with in different ways. But every single device, no matter which one it is, and when I get to this, I'm going to be talking about hardware and other things that we can use for recovery and why we would use those versus free stuff. There are free items, and probably till we hit about 2006 or 2007, a lot of free items and paid items were very similar. And now we've crossed the line. There's a lot of things you can do with hardware devices. And when I say these, what I mean is the PC3000, the Atola, the DeepSpar. There's a couple others out there, like CPR Tools makes one. They're the only American company that makes a tool. This is not a sales class in any way. I'm not trying to tell you, I'll tell you what's good about every device, what's bad about every device, what you can use it for, what you can't use it for, and what you could do instead that would be free, because my opinion would be, if you could save money, let's try to do that for free. But there's some things today, economically, it just doesn't make sense. So I'm always going to be about how quick can I produce income. And so the return on your investment is going to be really, really important. Now, I know some of you guys are government guys, and some of you guys are doing, recoveries for forensics purposes and things like that. And the very first point of this class is going to be, if you're running a business and you've got to do this, what's the most efficient way? Because even in government agencies, I do a lot of criminal cases. I do police work. I do things from that perspective. I'm not a policeman, but from that standpoint, do some of the same things that policemen do. And time is one of the most important factors, because most of the time, you just don't have 18 months to work on something. Some government agencies do, but I don't normally. I have like 12 hours to tell you everything I can possibly tell you. And so that's going to fundamentally be my goal, is to make sure that everything is as fast as possible. So speed and the way that we communicate with the devices is one of the most important things. So when we're talking about ATA standards, all the earlier drives were all done through a programmed mode. I mean, somebody had to write a piece of code to do every single thing. It was like that with even video drivers. If you wanted to play a game, you had to write your own video output. You did not just go into Windows and play a game. Like, that was one of the things that when Microsoft brought out Windows 95, that was like, we're king now, because we have DirectX, we have the ability to talk to the hardware, and so we have video drivers, so you don't have to write them for your games. Prior to that, everybody had to write their own video drivers. They had to write their own communication drivers. Everything had to be done by hand. So Windows 95 comes out, and now they actually have a way to talk to hardware. And so this is where we start looking at some of the ATA standards and how we start communicating with devices and the things that are important. I'm only covering the things that are important. These standards are huge standards. There's a lot of content in them. And there's a lot of commands. There is a lot more commands than we're going to cover. Back then, you would have to have a tool to enter in your own commands. So if you wanted to actually apply a command to a particular drive so that you could recover data, you would have to go find out what that command is, look it up, and say, oh, this is a Western Digital, I need this command to do this. Now, today, this is where efficiency takes place, where a lot of the tools that you would buy or use have those commands for you. So you don't have to enter them. You can now click a button and select it, but it applies those same commands. So one of the biggest ones is when we move to DMA. When we move away from PIO mode, and having to write a piece of code for every single communication, we now move into a selection where we can actually transfer content, and this is about speed, through memory. We're basically doing a direct memory transfer without involving the CPU. Prior to this, all your commands would have to run through the CPU. So anything that you did that was programmed input-output mode ran through the CPU, and you would have to write a piece of code to do that. When we get to DMA, we now can evolve from a standpoint of not having to make that a processor-intensive item. We can now transfer data, and it makes it much, much faster. So again, we're talking Windows 95 from an operating system standpoint. We're talking Windows 95, and basically when we got to OSR2, we started switching to 32-bit, so we were able to actually communicate a lot faster. So, and then finally we get up into other speeds and other modes. But at that point in time, prior to the ATA Command 2, once we finally got to the ATA Command Set 2, we were calculating how we talk to our drive using something called CHS. There was actually 4 different modes that existed prior to the ATA Command Set 2. Now what that means is when your heads are going across the drive and you want to talk to a location, you had to know the cylinder, the head, and the sector that you wanted to talk to. You actually had to know these things, and you had to be able to control where the head was, on what platter it was. There were some manual things that we had to do back then to communicate with the drive and to actually control where those heads were. When we finally get to a spot where we're saying, well, let's get rid of, again, there was 4 different modes, so I don't want to cover all 4 of those because there was segments where from 504 megs up to 4 gigs and then up to 8 gigs that we could communicate in different ways. Once we passed 8 gigs, we had a problem in the fact that we couldn't address the space that we were looking for. So the ATA Command Committee decides, well, what we're going to do is we're going to switch to a new method of communicating to our drives, and it's called logical block addressing. Now, prior to IDE drives and prior to MFM and RL drives that we had in these early days, SCSI already existed. The Systems Communication Interface has already existed. Prior to this, it was used by Apple, it was used by other vendors, it was mainly mainframes and minis and things that used it as well. And all of this basically was stolen from SCSI. So all the stuff that we're doing now, IDE interfaces, in a lot of cases, if you look at a tool that tries to tell you what kind of equipment you're looking at, sometimes it'll actually say it's a SCSI interface, even though you know it's not, that it's IDE or it's SATA. They evolved from SCSI, and so logical block addressing, which means every block is in order from 0 to its highest number, that's how we're looking at them now. We're not looking at them as, well, we have CHS, so we don't care where our cylinder, our head, and our sector is. And I'll explain those things later. We'll get to those spots. Technically, even with LBA, logical block addressing, where everything is 0, and all they did was just put them in a row. Basically, that's all they did. And say, we're going to talk to sector 25. We don't care where it's at. We'll let the drive figure that out. So the hardware is now doing all of those calculations for us. And it's still a calculation that's based on CHS. We just don't know that. We don't see that. We don't have to talk to it that way. So LBA, we're just asking for a particular block. So we'll say, I would like sector 0, I would like sector 25, I would like sector 65. And we're communicating with it that way. And the operating systems are doing a lot of other work as well. And we'll get into that later as well. But the biggest one was we finally get away from all these older ways that we were calculating content, and we go to what's called logical block addressing 28. We're using what's called 28-bit mode. Now, that's how many bits we can count. There really were 32 bits, but they used 4 of them for reserved flags because stuff is done in segments here, where when we finally get to the next one, it'll be 64 bits, but they use some of them for reserved content, so it's 48 bits when it's done. So some of this content still gets reserved, but this is how we could address a drive. So 28-bit mode allowed us to address a larger drive. We could address a drive up to 137 gigs. After we passed 137 gigs, we couldn't count any higher, so we could not address the rest of the space. So if you guys remember back in the 90s, there was a time period where we had to go through this BIOS update because we crossed that boundary pretty quickly. From, if you figure out, well, 2000s, the early 2000s. So you had, anybody remember what size drives we had at the end of, say, 1999? Anybody remember how big they were? What was our biggest drive that you could buy? 1999.
256 meg?
What?
Was it 256 meg?
No, it was bigger than that.
Oh, okay.
That we would be back in the early 90s for that. So. How much?
Did we just hit the gig around that time?
No, we were still a little bigger than that. We made it to our average size before we changed our technology, because there was a change in 97 that wasn't really released till the end of 1999. It was 10 gigs was our primary we could buy 10 gig drives, but we started having some new SCSI drives that were 18 gigs, and then we started getting some 20 gig drives. But the 20 gigs and the 18 gig drives were based on new technology that just completely had been released as a new technology from IBM. And so those last few drives that came out in the end of '99 were not the same as what we were doing throughout the rest of the 90s. And I'll get into the technology side and what those things were later. But so that was 10 gigs. And then within 2 to 3 years, we're up to 120 and then 200. So by the time we're crossing into 2004, so our whole lifespan of hard drives evolved so quickly by the time we got to this new technology in 2000 that we crossed 137 gigs pretty quickly. And we had 200 gig hard drives. And if anybody remembers, there was a problem. If you got these 200 gig hard drives and you plugged it into your system without doing these updates, these BIOS updates, that all of a sudden your drive became 137 gigs. There was never a drive made that was 137 gigs. So that should be a clue. If you ever see that, you probably won't see it today unless you're going back into your storage room and you're pulling out some old computers and then trying to use them. You're not going to run into this 137 gig boundary, because it was a problem back then. It was actually a recovery process we had to do because it would nub off the partition structure. It actually didn't do anything to the drive. We just couldn't access the data. So the partition would correct itself and would just node itself at 137 gigs. But that's kind of one of those clues back in the day when I started doing recovery that we had to watch out for. But there is some specific things that happened with this particular ATA command that was really important. And so 137 gigs, you could use one particular command that you cannot use today most of the time under most conditions, and it's called ignore ECC. And the reason that this is important is this. When you have a sector that is damaged, so your head's moving along and it's reading a sector and the sector says it's damaged, your drive will normally return nothing. It will say, oh my God, there is a problem, I have a bad block. And so therefore it will just say, sorry, I cannot give you that data because it is bad. It is a guess. There is something wrong with this data. So we'd rather you not have a guess, we'd rather you have 0. And so that will primarily be what will be returned to you if you have an error. But as long as we had this ability, as long as we were using LBA 28-bit mode, we had the ability to say, I don't care if you think it's bad, give it to me anyway, and I will use that data however I see fit. So data recovery people had a command that was called ignore ECC. It's also known as a long read, but there's a problem calling it long read today only because it confuses people, because we now have something called a long sector, which we did not have back then. And so people get confused by which of those choices it is. So I'll try to break those down for you later, but it's called a long read, ignore ECC. And what this does is it says, well, you have a sector, and at the end of 512 bytes, there's going to be at least 4 bytes of ECC. And ECC is error correcting code. Basically, that means every time the drive reads it, it reads a little chunk of ECC and says, well, I've got some errors, either I can fix them, or I can't, and if I can't, then I have an error. If I can fix them, I'm going to either use ECC to do it, or I'm going to use ECC to verify that it's actually correct. Does everybody understand what I mean by this? I don't want to get too much into it. It's called a Reed-Solomon encoding format. It's a very basic algorithm for figuring out, kind of like parity, a little bit, if anybody knows how that works. It's a little bit like that, but not quite. But fundamentally, you could tell if your sector was bad. So if you send the command ignore ECC, it returned the data anyway. Now, one return of the data is bad. That data is garbled data. You don't know if it's right, you don't know if it's wrong, you don't know anything about it. It's not even a good educated guess. It just read data, it had no way of verifying it or doing anything, so you got delivered a chunk of something you don't even know what it is. But if you could request that data, say 100 times, now every time it reads it, you could start to compare it to the previous data. Eventually you know what you have, if it's right or wrong, or you can fix it. Because let's say 25 times it returns one particular number. Well, 25 times is a pretty good percentage of that out of the garbly goo that's going to come out of it. So if you could compare all the bits that came out, you could have the bits fall through, and you could say the ones that had the most of all the choices, this is the best possible guess. Is everybody with me? Everybody understand what I mean by this? So we're using an array to try to resolve this, but they're single commands. They're one command at a time, and you have to have a tool that's going to gather the content that comes from this array and then figure out whether or not you have the right answer or not. And eventually you can actually solve that, and it replaces the sector with that data. So you could have a bad, damaged sector that all your forensics tools, I know at least half of you have done forensics and used like FTK Imager. How many people use FTK Imager? You guys use it? No? Yes, yes, yes. So half of you have. Software tools that will image your sector, image your content. Well, those tools fail because they have no way of requesting anything special. They have nothing smart about them whatsoever. All they do is say, hey, Mr. Windows API, please give me a sector. If that sector comes back without anything else, there's no intelligence to it whatsoever. Even tools like Encase, where you spend $4,000 on a tool that is a forensic analysis tool primarily, has imaging components in it. My opinion is if you can't image it, then the data that you have is possibly bad as well. Like, it seems like it's more important to get the good data you can get and then to analyze it from that standpoint. But that doesn't seem to be everybody's opinion. We'll talk about guidance in a little bit. So at least from this standpoint, we have the ability to request a sector that's damaged and to do something with that sector. So that's pretty important, and we don't want to lose that. However, when they went to the next mode to get past LBA 28-bit mode, they went to 48-bit mode. And when they did that, they said, you know what? We have some commands that are obsolete. Let's get rid of these commands. And they did a checkbox, and they removed those as necessary commands. So in LBA 48-bit mode, we lose the ability to use this command. We do not have ignore ECC technically in anything past 137 gigs. What we have is a command that kind of emulates it when the data is dumped into memory. You can request the content from memory. But the problem is, anytime you're dealing with memory, if anybody's ever used, done memory forensics or done memory stuff analysis before, is that whatever the junk was that was there before, when the new junk comes in, if something doesn't replace the old junk, then you have junk mixed with the new junk. So you have junk. You have a lot of junk. So that's pretty much the way that goes. So you have to be really cautious about this. So the new command that you could use actually pulls it from memory from the hard drive instead of from the sectors themselves directly. So this is more accurate in LBA 28-bit mode for the first 137 gigs. And then after that, now we're up to 10 terabyte hard drives and possibly 16 terabyte hard drives. That space isn't going to get looked at the same way with the same commands. Fortunately for us, the most important data of any hard drive is in the first 137 gigs. And you have to take that a little grain of salt from that standpoint, because it depends on where your partition is, right? Because if your partition is 2 terabyte into the disk, and the important stuff sits there 2 terabyte into it, you may still be in the first 137 gigs of that 2 terabyte area, but now you're 2 terabytes down, so you cannot use this command to help you in that particular area. Does that make sense? So you have to start thinking these things through from that standpoint. If it's the beginning of the disk and it's in LBA block 0 through 267,000 something. So at least from that standpoint, we have a command that we could actually use that would evolve and give us more data. In ATA 3, we developed a SMART standard, and SMART actually comes from an IBM technology called Self-Monitoring Analysis and Reporting Technology. And that content was primarily for us to do preemptive checking on our hard drive. It's actually a very fluid, very robust set of technology, but people think very poorly of it. And the reason that they think poorly of it is the fact that SMART has been made dumb on purpose. If you have a hard drive and you have a system that can tell you, hey, your hard drive's going bad, and let's say you bought it 90 days ago, who has to pay for that? If your drive is going bad and your system tells you it's going bad, who's paying for it? The manufacturer's paying for it. What does the manufacturer not want to do?
Pay for it.
So they made Smart stupid on purpose. They turned it off in a lot of positions. They make the code. So this is one of the other problems with Smart as a whole, is Smart was designed with this whole plethora of testing and processes and things that we can do to tell us if there's something wrong with our drive before data goes bad. But if that happens and the manufacturer has to pay for it, Smart does not have a specific requirement for what the code is. In other words, when you write your own code and you put it in your device, there's no specific requirement that says you must do this. It's like, here's what I send you and here's the result you can send me back. And they write their own code. So they're not required to do anything that could actually say, hey, my hard drive's going bad. So they remove some of the commands, they remove some of the stuff, they make it stupid. It has some real advantages on the ones that work, but one of the other big advantages we have is that, and I'm going to jump way ahead, and I'm going to talk about stuff that has, I have not covered. I do things by redundancy, so this is the chicken and the egg. There's no way I can tell you what a chicken is till I'll tell you what an egg is. I can't tell you what an egg is till I tell you what a chicken is. So there's no way for me to catch up here. So on a hard drive is a full-fledged computer in and of itself. It has memory, it has a processor, it has controllers. It is as intelligent as your whole computer is and has been since the mid-'80s. It is a full-fledged computer. You could actually run applications on it if you could get to it. So all the way back to '86, it has been able to do these functions and these things and has been a full-fledged computer. It also has its own operating system. And when I say that, I don't mean Windows or DOS or anything else. The actual drive itself has firmware and content that's running, and it has its own operating system. It has its own tables. It has its own storage. It has its own ability to communicate with itself, check itself, do things. It's alive at all times. So it has a place to store data for its own tables, and that is on the platters. It is not on the board. There is a couple of items that sit on a board for some tables, but for the most part, the board is not really the part that matters. All the communication and all the content really sits on the platters in what's called a system area. And the system area is something we just agree to call it. The system area is not really technically a real thing. We kind of just all, as data recovery people, agree to call it that. Manufacturers won't give us the time of day. So most of them. So in this particular instance, when a table from Smart is read from the platters, we actually will know something that we don't know at any other point, which is we've read content from firmware. And that becomes a very important step for us. Even though maybe the data from Smart is useless to us, reading the data from Smart tells us something's working. And it's a really profound thing that we have because we have no other way of communicating with the hard drive without reverse engineering some of this stuff or using some really high-end tools. So just understand when we get there, those are going to be the primary things that are going to be important. So I know I'm giving you a lot of information right up front, and it's early, and people probably need coffee. So at the end of this page or the next page, I will let you go get some coffee, and then we'll do some intro stuff.
Hey Scott, can I ask you a question?
Yes.
Okay, when you get to 137 gig,
Yes.
and you have like 2 terabytes,
Yep.
and what do you do from there?
Well,
go to
because we can address the first 137 gigs using Ignore ECC, what I would want to do if I'm doing data recovery is, and you only do this in the final stage. In the final stage, if you've got sectors you cannot read, you would switch to Ignore ECC, and you would build an array. You would use a tool that will do this so that you don't have to do this yourself by hand. You can do it yourself by hand, but that would take a really long time. So there are tools that will now say, I'm going to read the sector, I'm going to build an array, I'm going to tell you the best possible choice, and I'm going to write that back as a sector. But once you pass 137 gigs for the same problem, you will now have to use, it'll be a 48-bit mode, which then will read from memory of the drive, and then do the exact same thing, but it'll do it from memory. So your accuracy will drop. It will not be as good. But your guess of the data will still be better than 0. See, filling 512, and this is the real problem too, is we have switched from a sector that's 512 bytes. For now, for eternity, I'm going to say sectors are 512 bytes because the hardware that you're using is basically peeling off 512. They're reading bigger chunks, but they're just delivering 512 to you as that's the only way that your OS can talk to it. Right now, all OSs can only still talk directly at 512 bytes. That's all they can do. So there are bigger sectors, 4K sectors. And if you have a problem, you have 4K errors too. That one sector is a huge sector. So now you have a huge problem. So that content's being read into memory, and then you're reading out small chunks of it and trying to build an array and correct that data from something that's damaged. But 0, especially for 4K, that's a pretty big chunk. If you have a JPEG, if you have a picture and you have JPEG, and you have 512 bytes of zeros, you might see a blemish in one little spot, but you have a 4K block of zeros, there's a chunk missing. It may even throw the entire algorithm off so that you can't even see the picture anymore, that part of the picture is completely destroyed because it completely shifts. So if I had a guess that was there instead of zeros, it's potentially possible that you may not even notice that there's anything missing at all if the guess was halfway good. Does that make sense to everybody? So, and that's the same thing with a lot of other things right now. Like for instance, really Microsoft Word documents are using something very similar to using a zip file at this point. So you can actually correct a lot of Word documents based on the patterns and the content they actually have. So there are things we can do to correct files that we cannot recover a small chunk of data from. But my first go for everything is going to be get the best data possible at the beginning. The people who are doing forensics and they image a drive and they get 150 sectors that are 0, in my opinion, you didn't do a good job. And the reason is the tools don't do a good job. But you need to know that, and you need to know that this is a problem and that there is something I can do about it. And I've had a huge fight with guidance about this because guidance and Encase, Tableau, they know this. They don't want you to know this. That's my opinion. And they'll do everything they can to stop you from knowing that there's other options that you have because they don't want to spend the money. They don't want to buy another company, and they don't want you to know that other companies exist, so you buy their tool instead of theirs. So we have some proof. And we have a person sitting in the class that will profess this at lunch. So, okay. Everybody up so far? Did I answer your question?
Yeah.
You good? So, and I'll teach you how to do this. This is the entire premise. This is just the first half hour. So, but this is the entire premise of what we're going to do all week long is get everything we can possibly get the best possible sectors, the best image. Let's talk to it however we can. And there's a number of ways that we can do this with a number of tools, a number of different passes for free, for money, and it really depends on what the status of the drive is. And we'll get to that as we're going through some diagnostics and trying to figure it out. When we get to ATA command set 4 and ATA spec 4, they added an item called host protected area. Now, this to me is extremely important. Most forensics guys know what an HPA is. They've heard of a host protected area, mainly because their tool pops up and says, hey, I've got a host protected area, and every class that anybody ever takes for forensics says, that's where all the hidden stuff is, right? That's where every bad guy is going to store his data in every class that you've ever been in. So they must somehow get the data from the host protected area. And I'm not going to say it doesn't happen. It does happen. I've seen it a couple of times. But I don't know it was always on purpose either. That's the other problem. There's 1 or 2 times I'd say it was on purpose the bad guy did that. But most of the time I would say, the reason that the data's there is they had their hard drive at a different size, other stuff happened. What a host protected area is, and I need to make sure everybody has this very clear in their mind. It's a very simple thing. All it does is say my drive is smaller. It can actually say my drive is bigger. But what would normally happen is it's called cutting a drive. So if you have, and the reason this exists was because when Dell and Gateway and all those guys were releasing hard drives, they made an image of your Windows partition and they put that image on the drive. Well, there was not an easy way to expand or contract this image. You could not say, well, one guy wanted a 250 gig hard drive and one guy wanted a 40 gig hard drive. Let's expand that. They had to have a process to make drives when they would buy them the same size. So you can make something called an HPA. And what that does is that says, well, this time I bought a 60 gig hard drive, 70, whatever size hard drive that you want to say you have. And that hard drive can be cut down to a 40 gig hard drive. So if you have a 40 gig image and you wanted to use a 40 gig image over and over and over again, you could just make that hard drive smaller and tell everybody it was a 40 gig. It could be bigger. It could have been 100 gig, and they just cut it down so that you could use it. Now, outside that HPA, outside saying, here's your user area, and this is available to you, this first 40 gigs, they would store the DVDs for Windows and for the other stuff. Remember when they used to come and you used to get a whole package of stuff. You used to get a package of all your CDs and stuff to reinstall your system, and then all of a sudden you started getting systems and there was no package. And that's why. Because the packaging was expensive for them, and they convinced you, this is the really cool part, they convinced you, hey, you do not have to go and get this package of discs out. We have it stored on the hard drive for you. All you have to do is make your own discs with your CDR. And so they even convinced you to even go buy your own CDs and make your own copies of your own discs in the process. The manufacturer cut it out because it saved them money. And by adding this command, they could use space on your own hard drive. That's the other thing. They use your space to store your discs that you have to then buy CDRs to put on there. So they really did a number on you. But fundamentally, that's what happened. And we use this every day in data recovery. Every single day, I use an HPA. But in forensics, almost nobody ever uses them. They see them, they erase them so they can get the data from them or change them so they can retrieve data from that extra space. Because you have a hard drive and it's 60 gigs and you cut it to 40 gigs, you need to copy the rest of that 20 gigs and see if there's anything valuable out there. So you need to get rid of the HPA temporarily so you can copy the full 60 gigs or ignore the HPA. And we'll talk about that as we go. But I want you to understand it's very important that I could use any size hard drive I want to recover the smaller hard drive. If I have a 40 gig hard drive that you gave me to copy an image and I want to make sure that I'm doing it right, I could use any size hard drive. I can use a 2 terabyte hard drive and I can image your 40 gigs and then I set an HPA and then that tells all of my equipment, ignore the rest of the 2 terabytes. So I save a lot of time in processing only the 40 gigs. Because if there's a problem with a partition structure or something, even though it might only be 40 gigs, it's hard to tell your hardware to stop processing. Right? You can process a partition if you still have a partition. But if you don't have a partition and there's damage, it may be very difficult to stop at 40 gigs. You have to go manually enter stuff or say, oh my God, I'm at 60 gigs, that was too far much. And so what happens if you process the data that's past, what was in the rest of that 2 terabyte hard drive? Do you know? You don't know. Usually it's somebody else's recovery. That's usually the way that works. So in forensics, a lot of guys will say, well, we start with a sanitized hard drive, so it's already erased. But in data recovery, I have 8 drives coming in a day to process. I don't have enough time to erase and spend 2 days erasing every hard drive that I have. So what we do is we overwrite the data and then we erase the data we didn't copy, or we nub it off using an HPA so that 2 terabytes I don't have to spend a day and a half erasing. So we nub it off so that we can do that. Is that clear to everybody? So in forensics, you are supposed to sanitize your drives. You're supposed to make sure that they're clean to begin with. Doesn't always work. A lot of people don't always do it anymore. That's the other problem. It's kind of dying because of the size of the drives now. A lot of people buy a 4 terabyte hard drive. We don't have 4 days to wait for it to erase. So there's a lot of processes that are going on here that are either changing or have to change. But in HPA, all it does is say in Windows, in my system, it's going to say I have a 40 gig or an 80 gig or whatever I tell it the size is. I can make it be anything I want it to be. As long as it's a sector, I can make that sector. I can make it 1 sector. I can make the drive 1 sector if I want to make it that big. And the drive and Windows and everybody will believe that's how big it is, no matter what I say. It's artificial, but the equipment agrees that it will honor that. Everybody understand? So that's very important. We're going to use this all the time. There is a second one that's called the DCO. Device configuration overlay used by Dell and a bunch of other vendors, and they usually use that for like Unix utilities and things like that, where you're going to boot and test your system. But it's identical. It's the same idea. We just primarily always use HPAs. If you see DCOs, then that means you can have two. You can have both of them on your system as well. All they are is hidden from user. That's all that's all those content. All that content is. So we're going to talk more about that, but I want to make sure everybody's clear on what that content is as a whole. ETA 5. The reason that that's important is because a CF memory stick, compact flash memory stick, is the only memory stick, the only physical memory component we have that exists that has its own ATA spec. None of the others do. And what that means to you is, if you have a professional camera and you are using a compact flash device, it will be treated as a hard drive. We can do all kinds of really cool stuff if we can talk to it as a hard drive. We'll have to get an adapter to plug it into, but it will still show up as a hard drive. It's a bootable device without modifying it. It will treat it just like a hard drive. And anytime you get a compact flash, you should think of it as a hard drive, because your ability to process it will far exceed any other type of memory. So if you have an SD card, anything you plug that into, even if you can get it to plug into an IDE adapter and then plug it into your DeepSpar, plug it into your Atola, plug it into your equipment, it's converting it to USB and then converting it to IDE. So you really don't have control of it. You really are still dependent upon a USB chip to do that. All of them, all of the current technologies that do that are all the same. And so that's the one thing you should recognize, different than anything else. If somebody says, you know what I'd really like to do is have a really fast bootable system and use an SD card. Well, just tell them, don't use an SD card, use a CF stick, because that is going to be the real thing. The SD card, you're going to have to do some special tricks to even make it bootable. But you're only going to be communicating through USB. You're not going to be communicating through an IDE channel. And that's very important, okay? So there's a lot of people predicting the future death of CF, but I think it's going to be around for a long time, because professionals know this, and professional high-end cameras all still use CF as their primary media. So there's a bunch of others that have switched to SD cards, but there's a whole nother problem with SD, which I'll get into, which is has to do with size and format, and it's using exFAT. So anyway, so those are the basic standards. Then at this point, this is when we actually go to LBA 48-bit mode. So we're looking, 2003, 2004. We're getting past 137 gigs. We needed an update. We had new BIOSes. All kinds of things have taken place. And then eventually into each of the other possible things, from SATA, hybrid drives. Now, hybrid drives, that's a completely different arena. And we really have to talk about that in the solid state area from that standpoint. For the most part, hybrid drives for Windows systems are really just regular hard drives. You really don't have to, in most cases, treat them as solid state at all, but on Macs you do. So they're two different things. And so we'll get into those as we start heading into the OS stuff on Wednesday. We'll start talking about the differences between those two. So just to kind of summarize the important parts of these handful of slides that I just went through, is whenever we're dealing with a hard drive, we have modes of transfer that we can do that are very important. PIO mode and DMA mode. Now, DMA mode has like 16 possible options. There's DMA, there's UDMA, and each one of those has a spec. So there'll be, DMA up through version 3, I think, and then there's UDMA up to version 7 or 8 at this point. So there are variations of the DMA. I don't really care what those variations are. Those are just about finding what a sweet spot is. We'll talk about those as we get into those. All I care is that we're going to switch between PIO and DMA. And then we'll figure out what we can do with DMA as we break stuff down into smaller and smaller chunks. If you had a hard drive, you would be surprised at how many times that when you plug in a hard drive, it does not work because DMA mode is messed up. Whatever happens in this transfer, whatever the chips are that they're using, whatever the memory is that's on the board, it's the cheapest possible solution, it fails. When you switch to PIO mode, there is a lot of times that the drive will actually be able to be read using PIO mode. Now, there's a verification process that doesn't happen. I don't really care because it actually still works. So in the real world, regardless of what anybody tells you about the verification process, it works. And so PIO mode, DMA, two very important things. You can do these manually with Linux, or you can do them manually with a Windows system as well, but you have to know what you're doing or think about it. And most of you might not even realize this. So as an example, if I'm on a Windows system, and it's a little bit probably harder to find it in version 10 at this point, well, this is still XP. But if I was on a Windows system and I wanted to switch my drive to see if I could actually do recovery without having to work really hard at it, I can go to my ID interfaces. I'm going to use the secondary adapter. You can go to advanced settings, and you'll see DMA and PIO mode. Now, if you were running a Windows system and you just wanted to play it, like in other words, we're doing this a poor cheap man's way. We do not have any special tools, and we're not going to, spend a lot of money. I flew to another country. I don't have any other tools. What am I going to do? I can go download a Linux distro, and I could do HD parm and enter a bunch of things. This is not a command line driven class. I'm just going to point that out right now. I'll tell you, I know the answers, but I didn't want to teach Linux in this class either. So from this perspective, if I had a Windows machine and I wanted to try to make something happen with a hard drive somebody hands me and says, well, show me what a whiz you are. Well, okay, I have no tools, but here's what I'm going to do. You don't want to do this on your primary controller. You want Windows to boot on your primary controller. If you switch it to PIO mode, it might not boot for a week. It could take a while. So you want to have a secondary controller, which all your motherboards are going to have a secondary controller in them. None of them are going to be without a secondary controller, but you can always buy a secondary controller and get it cheap, probably even locally at your local computer store. You can go get an IDE controller. Then you go into your drivers, you go into your IDE controller, and you switch it to PIO mode. You hook your hard drive up to that channel, and then you start to try to do a recovery from it. It's going to be a lot slower. But you might be surprised. There'll be a lot of times DMA does not work because there's something wrong with the board, something wrong with memory, something wrong with the equipment. And this will solve that problem. It's just one of the possible solutions that you can whittle away at. I just want to make sure everybody's aware that these things exist in other systems. You could probably get through a small pile of hard drives that you have sitting on your desk that are broken now by using one, if not a whole bunch, of the methods that we're going to go through, as opposed to an automated solution where I'm going to say, well, we have a tool that can do all 20 of these things and do them in a row. Does that make sense? You can do them one at a time, but you need to understand this is like I need to learn how to do math before I use a calculator. And those are going to be the functions. You can do these inside of Windows. There'll be a lot of functions that actually exist inside of Windows, but your problem is you can't communicate outside the API unless you're in PIO mode. That's the other problem. The Windows APIs will only allow you to communicate through DMA mode because they're doing big transfers. If you switch to PIO mode, you may actually be able to get outside of the Windows system itself and communicate with your drive. But if you have a 2 terabyte drive or a 4 terabyte drive, that might take you a year to recover. So we have a speed problem as well that we're going to have to deal with. Everybody understand? Good? Okay. Then after we're past PIO, DMA, the other modes are important are LBA 28-bit mode and LBA 48-bit mode, because those two have different commands. They allow different things to happen, and then not every drive supports all the modes. That's the other problem we have. So if you get a Samsung drive and you go plug it in and try to use 28-bit mode to recover the errored sectors, well, good luck, because it's going to abort every single sector. Samsungs are some of the worst drives made. Luckily, they're no longer technically made. They got bought and they're technically gone now, but we still have a huge slew of drives that are out there, and they still come in all the time in data recovery stuff. I'm getting stuff, it's still all the way back to the early 90s. I'm still getting drives that show up that are 10 and 20 gigs that show up for recovery. Some of the guys who have had them in systems back, even 40 gigs, common stuff. I probably see more of those than I do. There's the subset in between that's missing. There's all the old stuff that existed up to, say, 200 gigs or so. Then there's like a huge gap that skips until you get to like 1 terabyte up to 4 terabyte. And so you get a huge chunk of those and a huge chunk of those. and the others just kind of trickle in the middle. And the reason I think that happens is I think a lot of guys might have, oh, well, my computer's got a 40 gig hard drive, it's been running great, I really don't need it. Wow, there's a system with 4 terabyte? I really need that. All of a sudden I need to copy all my DVDs onto that hard drive. And so I think they're going from that to that. I don't think there's a lot of in between where somebody goes, 40 gig, 200 gig, I don't think so. I don't think they're really struggling for that kind of upgrade. So you'll get a whole bunch of them that are in the middle. But just understand, all of these different modes we're going to use, they only work in certain situations with certain drives. They don't work for every drive, every model, every brand. They're all different, and you have to think of every single drive as a unique entity. It's going to be different than anything else. Okay? So, and I did hit the host protected area pretty decent. Just to understand with host protected area, the entire point is for us to cut the hard drive down so that we're not processing the rest of the drive. There's one fundamental reason for this, and it's because the last hard drive I recovered might be 2 terabyte, and I wrote it to this 2 terabyte, and now I'm working on a 40 gig hard drive. The guy who's the 40 gig hard drive, we don't want to give him the data that was out there on the rest of the 2 terabyte, because that doesn't belong to him. And he's going to be really upset when he gets somebody else's porn. And that's usually what happens. That's where all their porn is. So from that standpoint, that's what we're dealing with. We're dealing with something that we just want to make sure we're only processing the small amount. So it is a habit of mine to constantly set the HPA at the end of every recovery so that I'm only recovering the stuff from the drive. And I can always tell the people that mess it up. It's really easy to tell. And a lot of the tools will ignore the HPA when they're imaging. They don't force you to set it. So almost every tool that's out will allow you to image content past what an HPA is. They'll ignore it. Only Windows is going to look at it. And when you're doing a logical recovery, that's where it's going to happen. Because we're going to have stages we're going to go through. We're going to go through one stage where it's going to be we're diagnosing, we're fixing, then we're starting our image, we're recovering the content, then we're going to plug it into a Windows system or a Mac or Linux, and we're going to logically recover the data so we can give it to somebody. And it's only that last stage that most people think that data recovery is. And technically they're right, but there's all this repair stuff that has to happen before we get that far, or we're not going to get any data. So there is a command that allows you to set the size and then set the size back to what it's supposed to be. So you have the full size drive again. And same thing for device configuration overlay. We won't use this on a day-to-day basis. They may exist on drives. We won't use device configuration overlay. We're going to use HPAs. So these are going to be the main things that we're going to use. So, everybody grab coffee, get some energy, and then I'm going to do the intro stuff so everybody knows about the class, what we're going to do. I just wanted to make sure you guys see we're hitting the ground running. We didn't start with the fluff. Okay? All right.
Did we take these?
Yes. Yeah, I'll tell you all that in a few minutes.
Mark them all off.
Yep. Yes, that's yours.
Thank you.
Okay?
Is there a DVD too? No, I'm sure.
There is a...
Tanya mentioned like
yes,
days or
I'm recording all the material, and we'll hand that out